So Jérôme and myself will talk today about variable extended precision, and we build it in a Risc accelerator, and we are targeting HPC scientific applications. So here we are. So Jérôme and me are present today, but there are other people in the team. We have Yves, which is more working on application levels, which is he's a numerical analyst information. We have also people working more on arithmetic, designing high-speed floating point units and things like that. We have a full team of designers and verification of hardware. And so Jérôme working on the software side. We will talk a little bit about this later. And myself, I'm the lead architect of this project. So more working on hardware side and sometimes also lower levels of software, such as abstraction layers. Okay, let's start. Just to present ourselves, where we work. So we have a department inside CA LIST. So LIST is, let's say, the software institute of CA. But we are more working on hardware in our department. We are about 150. We have two actually locations, one around Paris and one in Grenoble. So Jérôme and me are in Grenoble, located in Grenoble. And okay, just to give you some ideas, we make about 25 patents per year and 100 publications. So as I said, we propose extended precision for HPC application, and namely linear solvers. We'll focus on this now. So the starting point is PDE equations. You probably know this kind of thing, and we formulate them in a variational form. So we can find this kind of formulation in a lot of domains: computational physics, climate models, also more industrial topics such as CAD tools, electromagnetic and fluid dynamics, and also some optimization algorithms that also rely on linear solvers. So the flow is generally like this. You start from your equation, you discretize them, you have your very big matrix input. You manipulate the matrix to, for example, for preconditioning, and then you solve. So either you try to solve AX equal B, or you want to find some eigenvalue. So EVD, SVD, and also block solver sometimes depending on the application. And generally, you spend most of the time in your solver. So that's what we are targeting. And it's interesting that in particular for iterative solvers, round-off errors may prevent or delay convergence. And we are working here to try to improve this convergence. So first, why extended precision? So you probably know the radix-based floating point representation that is used in hardware. So you have your mantissa, which is on p bit, and your exponent. And for double precision, so you have 52 bits of mantissa, 11 bits of exponent. And our processor actually supports from 3 to 512 bits of mantissa, so much bigger than double. And also bigger exponent, we can go up to 18 bits of exponent. And the idea behind our work is to specify this at runtime. We don't want to recompile the application when we change the precision. So we want the same type, whatever the precision. And we are aware that the trend is actually to lower precision. So in artificial intelligence, we want to go as low as possible, even 1 bit of precision sometimes. But yeah, we think that extended precision is very useful for this particular application in HPC. So again, you probably know the issues with floating point computation. As obviously the hardware is fixed size, you have rounding issues. So for example, here I show the addition of two floating point numbers. The first thing you have to do is to align the two mantissas. So for example, here we have beta, which have an exponent which is 50, which has a value of 50 lower than the alpha one. And so you align beta by shifting the mantissa by 50 to the right. And okay, it may depend on the actual hardware, but generally you ignore actually the less significant bits of your smaller number. And it leads us to have floating point addition, which is not associative. So it is very difficult to use properly. And at least in iterative methods for linear solvers, on large problems, it can lead to issues with difficult convergence, I've said earlier. And we think that extended precision can address these issues. So initially, we started with trying to find a case study for this. So it was maybe 8 years ago, we worked on this study. And we come up with this application, which is a fluidics application with an 8K by 8K matrix, which was output from an incompressible flow simulation flowing above a cavity. So it was a particularly shaped cavity, which gives us a very high condition number, so very badly ill conditions. And we compare between 64 the solution with 64 bits of precision with preconditioning and 192 bits of precision without preconditioning. And the very important thing is we don't increase precision of the matrix or the right-hand side vector. It stays at 64 bits. What we increase is the precision of intermediate vectors. So for example, in the conjugate gradient algorithm, you have 5 intermediate vectors, or in the B conjugate gradient, it's 10 vectors. So that's the only thing we increase in precision. So here you see the difference in the velocity field between the two solutions. So there are some difference, but it's actually the difference is lower than 64-bit precision, so it's very small. But the important thing is that we reduce the number of iterations in the conjugate gradient. So we converge much faster. So here 40% faster. So as I said, extended precision is not intended for more precise results. It's just to increase the convergence. But we still get better result, but better, we don't know what it means because it's very small in here. So maybe it does not have any physical meaning. And we actually found better, more interesting applications where even at 64-bit, it did not converge. So here you have an example, for example, an ultrasonic frequency domain breast tomography. So we are using block B conjugate gradient to solve this. So it's a direct solution. The matrix is much bigger than the previous one. And here we show, for example, the solution for one of the sources. We put sources around the breast tissue. And here, as we are doing tomography, you can actually work with more or less sources. And the more sources, ultrasonic sources you have, the faster the convergence. But it's also harder to put into use. So if you can work with a lower number of sources, it's also better. And here you see, for example, with 4 ultrasonic sources located around the breast tissue, you even don't converge at quad precision. So you need 256 per bits of precision to reach convergence. So these are very interesting problems. And actually, the state of the art on this kind of problem is to use a time domain representation for the problem, so for the matrix. But here we are using the frequency domain. So the matrix is much more compact actually, and you need less data because you start from your frequency, your FFT result, instead of having your ultrasonic measurement in the time domain. And we also used standard matrices extracted from the sparsute set of matrices. And we solved them actually on our hardware prototype this time. So here the state of the art is to use complex preconditioners when we don't reach convergence. And we show that with conjugate gradient without any preconditioning or only using the Jacobi preconditioner, which is really simple for the X10 and NASA matrix. We have convergence much faster, and also sometimes we need to go at very high precision to even reach convergence. For example, here for some matrices we need 192 bits, and even for the X10 we need 384 bits of precision to reach convergence. So it's very interesting that it showcases that very high precision is needed in these cases when you want to avoid complex preconditioning. Up until now, we only spoke about iteration number. What does it mean also for the execution time? So again, running on our hardware prototype. And here what is interesting is our hardware goes slower when you increase the precision. So there is, and so you reach some trade-offs. You have a competing effects here. By reducing the number of iterations, you go faster, but at the same time, each iteration which takes longer. So you start to see some sweet spot. So for example, here 128 for the random one in conjugate gradient, or for X31, you need to reach, the sweet spot is at 256 bits of precision. So this leads us to what is our accelerator. So our goal is to integrate our accelerator into the compute node with the compute node. So very tight integration with the compute node, either in PCI Express or CXL, and or even in the compute node. So we actually work on these two types of integrations. We have actually made 3 versions of our hardware already. So we are now working on the VXP hardware. And what is now taped out is the VRP, and which has been also published. We have a publication at the beginning of this year in transactions on the computers. And okay, the VRP has been taped out in 2 technologies. So the first one, an older node from the Global Foundries in a test chip from the European Processor Initiative project. And also we will have the VRP core in the RIA chip from Cyperl. Just this time in TSMC7, so much smaller node. And our accelerator looks like this. We started from a Risc5 core, so we used the Risc5 CVA6 core from ETH Zurich. And we integrated an extended precision floating point unit in this core. So here you see the various units. We have a load store unit, some arithmetic units also. And our performance goal is to be limited by memory boundaries instead of arithmetic. So this is what we try to reach. So the main modification we did, we added a new physical register to store these very high precision numbers. So here it's quite big registers. We introduced register renaming, which is used for out of order execution. We modified the L1 cache to a better higher performance L1 cache, and introduced our floating point unit. And as I said, the main thing about our floating point unit is that it works iteratively. So it works on 64, on 128 bits of chunks. And so performance depends on precision. So both latency and throughput depends on actual precision you want. So for example, here load store performance, here is the throughput in terms of instruction per cycle. You see it decreased by steps of 128 bits up to 512 bits. And if we look a little bit higher at the GMV performance, so BLAS dense matrix vector multiplication, you see the decrease in performance when you increase precision. But with the VXP, we have worked a lot on this, and actually the reduction is much lower in this case. So Risc5 is nice is that you can add extension, ISI extension. So we actually propose a new ISI extension to support this extended precision computation. And again, the goal was to have no recompilation of the binary when you change precision. So what we did is we propose a new instruction that are parameterized with another actually register file, which is providing the output precision and also the rounding mode in this case. Or for example, for memory accesses, we are storing in this parameter the in-memory size, the exponent size, the rounding mode, and the stride for the indexed access. Because something that we noticed earlier in the project is that as we are dealing with variable precision to compute the address, it can be costly to use actually integer multiplication. So we do this computation inside the instruction. It saves us some instructions, and it's much faster like this. In memory, we use the IEEE extendable format, so very standard high precision format, and we propose this arithmetic instructions. And our compiler is still work in progress, so we have binutils, so we can compile assembly and also decompile. And we have a prototype LLVM Clang compiler, which has been done in a PhD by a PhD student, but it's still a very prototype thing, and we target to increase maturity of our compiler. In terms of hardware prototype, so we have had several tape out in GF22 technology, and soon we hope in the Cypher RIA chip, which will end up in the Jupyter HPC. So this is done by the Cypher startup, and we have 2 tiles in the. So it's not, yes, it's 80 ARM cores, I think, something like that. And we have 8 VRP cores in 2 tiles in this architecture. So we hope to have it by end of next year. And we also have a VRP FPGA prototype, so a VXP now, but we have a FPGA prototype with a dual core. So maybe, Jérôme, you can now speak a little bit about the software stack.
Thank you. So to help users to use this accelerator, we have also developed some kind of software parts to allow to create numbers in the variable precision format. So in the application side, it's also possible to declare like that some arrays or scalar types, precising the exponent size and the mantissa size of each element, and call some kernels that are fully coded in variable precisions. So these solvers are ported in a different environment. We also developed some optimized BLAS in assembly that can run on our hardware prototypes. And it can also run on a hardware simulation environment like Spike for the Risc5 emulation. And to tune the application and make it easily to develop, we have also a port of all the solvers quite transparently on the x86 environment with MPFR library. So you can see that in our BLAS, we have all the intrinsic linked to our ISA. and we can enrich and add additional operation by writing some extended assembly code. Where we want to put our solution is maybe just under existing library by sometimes and using our predefined type for variable precision, or calling transparently our BLAS or solvers algorithm in the existing libraries. So what is the variable precision SDK? It provides a set of primitives that allows some developers to write some arithmetic operations on scalar scalar numbers, and call some BLAS operations such as GEMB, scale, xpi, and other one to allow to build their own solvers. But we also provide some optimized solvers like BTG, BCG stab, and other ones that allows some more complicated applications to take advantage of the variable precisions. We support two use cases. One is to create new applications on non-accelerated platforms by calling VP float scalar operations and BLAS operations on the MPFR emulation environment, or call our pre-compile and optimized kernels on VXP platforms. The platform we support is of two types. We have a dedicated device with memory architectures. That's mainly on FPGA platform that we have as prototype in our lab. It uses a PCI bus to exchange data between the host and VXP accelerators. And we have another platform that is shared memory architectures. That is the model that will be implemented in the Cycle REA1 processor that use an IOMMU to exchange data without copying them from the host memory to the accelerator memory. Hopefully it will be integrated in the REA and available in Jupyter in a few years. How we deal with the offloading procedure by using the PCI bus is we provide a kernel interface to the application, which is quite transparent for the developers, and it allows to deal with offloading or not by selecting environment variable. And if we choose to not offloading, it runs through MPFR emulation. And on the other side, if you choose to offload, we flatten the argument of the kernel. Then we copy them to the VXP through the PCI bus. We copy the kernel binary that is precompiled from in the host into the VXP. We start the VXP and we wait for the completion and go back to the application by the same way if it was running through MPFR. What the component that we provide, that we use, is a VPSDK compile on Linux for the MPFR part and for the offloading part, and Risc 5 bare metal platform that allows to use the same type in the host and in the accelerator. That allows us to run solver either on the host with MPFR or in the VXP in native language. We have a dedicated Linux VXP driver that is used to deal with data copy, PCI interaction. It is mainly built on an existing driver from Xilinx that they provide for the FPGA platform, which is XDMA. And we need also on the host platform a Risc 5 cross compiler to be able to build the kernel for the VXP accelerator from the x86 platform. In the case of the shared virtual memory, we have quite the same interface for the application. but we have no more copy from the host to the accelerator. So what we do is allocate a new space of memory in the shared memory between the accelerator and the host. And then we have also a precompiled but not fully linked kernel that is relocated for the newly allocated memory. And then it is read and written at the right place in the memory. Then we kick the VRP with the data that are also in the memory and come from the user application. And then in the same way, we wait for the completion. But in this time, it is through an interrupt mechanism that is provided by the ARM platform or other platform that can use the accelerator. In this case, it is the ARM Geek. What we use is the same thing that the previous version is the VP SDK and the compiler. And what we do is in the Linux environment is using the VFIO Linux driver to deal with the IOMMU configuration and to avoid the copy from the data that are in the virtual user space of the user application and the hardware memory space that is used by the accelerator. Currently, we are working on the port of our environment through OpenCL. That it will allow users to code their own kernels quite easily. And we are based on the POCL distribution for OpenCL. And we have built an additional driver to this environment to deal with our existing PCI driver for the VXP. And it's quite friendly integration. It's quite easy to deal with the sequence of the OpenCL and what we have previously with the FPGA environment to deal with data copy and data retrieval. And the things that is quite interesting is that by using OpenCL, we are able to create kernels dynamically and deal with kernel argument discovery automatically through OpenCL and to be much more flexible for final user development. What we want to do for future work is to have a full compiler tool chain to avoid to write assembly code or optimize kernel by hand. It allows us to have a more efficient Scala operation to avoid to deal with registry configuration each time we have to do an operation. And it's something that is mandatory to provide this accelerator to our end users to avoid to deal with the assembly and all some hard aspect of the VXP programmation. And after that, maybe we can think about using OpenMP offloading because it avoids to have separate code for application and kernels. And it should be more easily for have an application that runs on the multi-platform.
Okay, I will end the talk. So just to summarize a little bit, what we have seen on the scientific application side. So we have shown actually that it improves convergence of iterative linear solvers. It is also useful for other kernels that I didn't talk in this talk, but there are other things we discovered and which are interesting. And in some cases, at least, we know that it reduces energy to solution because we are reducing the number of iterations, basically. And we believe it's something we have not yet completely shown, that it reduces also the energy to solution in the general case, especially by avoiding costly preconditioning techniques. So it's something we have not yet completely evaluated because we need to deal with the very big state of the art of existing preconditioners. So it's quite difficult to do. And also it reduces time to solution by improving reliability of linear solvers and eigensolvers. You don't have to maybe change your preconditioner if it does not converge and things like that. So you also not just at the time of execution, you also save some time on the people using the solver. Some open question we have still is that we don't know the right what would be the right precision before solving the problem. So it's something, and actually there is no theory that could be helpful there. Yes, we could do it by having the full profile of eigenvalues, but if you have it, you already solved your problem. So it's not very interesting. We also don't know which granularity we want to provide to the end user. For now, we can change the precision bit by bit. So you can have whatever precision at bit level. You can have 193 if you want, but it may not be useful. Actually, on our side, when we day to day, we only use 64 bits multiple. So maybe just focusing on this would be enough, instead of having the full set of configuration. Also, we don't know the impact of higher precision of results, as I said earlier, but it does not have any physical meaning, but maybe it can still be useful. On the hardware side, so we have demonstrated our FPU implementation, so we consider it solved. It's as I said, it's iterative chunk-based design, so performance depends on precision, and it's needed to have a FPU that is not too costly in terms of area. And again, the lower arithmetic intensity of targeted application should make it not very costly, because you probably don't need a lot of arithmetic performance to saturate your memory. So the overhead should be, in terms of system, should be quite low. We have demonstrated the integration in a RISC-V CPU with an ISA extension. What we have discovered is that we need either a wide reordering out of order window or a highly simultaneous multi-threading system. So for example, a GPGPU, because we have a quite high latency arithmetic instructions. This is the kind of latency you generally see when you access memory, but in our case, it's also for arithmetic computation. And the challenge lies in the memory subsystem, having high bandwidth caches, interconnects, and also high bandwidth memory controllers. And we are working on streaming accelerators, especially targeting the sparse matrix vector or sparse matrix dense matrix multiplication, because in this case you have let's say quite random memory accesses, and it's not nice for the cache subsystem. So we are working on dedicated accelerators for this. So wrapping up, so today we presented our activity on extended precision for scientific computing, but our team is also working on other things, which for some of them could be relevant for CERN-CAF. For example, we are working on 138-bit Risc-V extension. So here you may be able to address the full memory range of your supercomputer, so having a shared memory from all nodes. And we are also working on heterogeneous integration with GPUs. So we are working here using the open source Vortex GPGPU, also Risc-V based. And some open source coherence protocol, Open Python. So this is a work we are doing in collaboration with UCSB and Georgia Tech. And to conclude, we are open to collaboration, so don't hesitate to contact us. Thank you. And I can show you here the publications, list of publications. So
it looks like a rich set of reading for people to do.
Yeah, because it has been several years we are working on this, so a lot of publications.
Great. Well, thank you very much, Eric Jérôme. It was a very interesting presentation on a level of hardware that we don't often think about, actually, but it's interesting for us to do so. So very happy to now open things up to questions or comments. People want to say something? Just raise your hand on Zoom. Maybe I'll start then. You mentioned that perhaps instead of offering, bit by bit precision, you might be able to offer a stepped precision that would go in some, power of 2 or something like that.
Yeah.
Would that help simplify the design a lot? It does only support that.
Yeah, actually, yes, it would simplify the design, especially when you think about memories, extra memories. When you do error codes for error detection and correction codes, generally they work on 64-bit chunks. And so having to deal with bit precision, you would have to do read, modify, write in a lot of places in the design. So yeah, it's quite costly to have this kind of precision actually in terms of configuration. Yes. So it could, it will simplify the design.
Okay, great. Yeah. Any other questions? Maybe I'll ask another one about software, which is about the. You showed that you keep a lot of the end result of the calculation is kept in 64 bits.
Yeah.
But you have some representation for the higher precisions on the host side as well?
Yes. Okay. So it's related to the work we are doing with OpenCL. For now, we are offloading full solvers. So, and everything is working on the VXP. What we are targeting in the end is to have the same memory representation, so using IEEE extendable also on the host side. So it will need to deal with conversion with the MPFR memory representation. But the idea is to be able to, for example, do some scalar computation on the host, because in your solver generally you have blast calls and some scalar computation, some division in the middle. And if for now we offload the solver, but we would try to offload only blast calls. And in this case, having the possibility to run some scalar code on the host also with the same memory representation would allow to seamlessly offload blast call and merge computation between host and accelerator. So it's a final grain offloading, and it's not yet implemented, but it's something we are targeting in the end. Yes.
Okay, yeah, I think that could be interesting for us, because in a lot of our problems, it's very hard to pin it down to one computational kernel that's going to consume 80% of all the CPU time. It's much more like a kind of like a sort of power law of maybe a couple of things that are up at the 10, 20, maybe even 30% level, and then a long tail. So being able to chain some different kernels together would probably be quite interesting for high energy physics. Yeah, so that would be good. Okay. Other questions, comments from Zoom in the room? Okay, well, if not, then I want to thank Eric Jérôme. Yes.
Yes, I've written a few questions in the chat, but I can say them.
Sorry, I couldn't see the chat. I was looking for hands being raised on Zoom, but go ahead. Thanks.
Sure, no problem. So probably my first question is, what software profiling options does VXP offer for now? For example, do you have any hardware performance counters that can be used, etc.?
Yes, actually, it's something we implemented quite recently. Yes, so we have the standard let's say, performance counters from Risc. So we are using CSR accesses so to get some performance. But we also developed a dedicated performance counter IP, which is very nice, I think. I'm not objective. and it's something we integrate with the core, and I think we have something like 120 sources of events, and we can do some live histograms on with some periods of time, and so you can do a lot of nice things with this. And yes, we have an IP to do this, and it's not limited actually to the VXP. It's something we intend to use in other cases also.
Okay, and another question: does your SDK support only C, C++ for now? And if so, do you have any plans for adding support for more languages? Because I've seen in your presentation that your work touches LLVM, and LLVM is not only about C and C++.
Okay. So for now we only support C, C++. We are also using Julia, but in Julia we are templating the BLAS with. I'm not expert, but I think you can template the Julia BLAS with a higher precision. And in the end, it's also based on MPFR, but it's separate from our MPFR SDK, so it's something we use for prototyping, application prototyping. But we would like to also use the Julia FFI to call our solvers in extended precision. So call our C++ solver from Julia code. So it's something we intend to work on also to ease the use for end users. So it's something we are thinking about. Yes.
Okay, thank you. And
Thanks,
also
Max.
thank you very much for the very nice talk.
Thanks.
Yeah, thanks, Maximilian. I just gonna chip in a comment there that, of course, Julia's type system is very nice for handling additional types of real numbers and floats that might have.
Yeah, but what you are seeing is that it's still not as high precision as doing, for example, in our C++ code, we use eigen templated with MPFR, and it's still faster, especially regarding parallelism. We can use also OpenMP and use some pragma from a PNP to parallelize things, and it's still faster. But that's why we intend to use the FFI to call our solver from Julia. So instead of using the templating system from Julia.
Very good. Okay. Well, last call for questions then.
Maybe just one. You mentioned OpenCL for hardware abstraction. Did you have to do anything special to this? Are you maintaining some code on this, or is this all done?
We are using Pockle, so it's an open source OpenCL provider. So it's a platform available and which has a lot of targets already, and also we are adding a new target. But obviously, the OpenCL C language does not support extended precision, so we are still we still have to. So for now, we are using our assemblies, so we don't have a new C type. But if we were to merge, let's say, our OpenCL work with our LLVM-based compiler, yes, we would introduce a new C type in the OpenCL C language, which is not standard, clearly. So yeah, you would have to do something on your kernel code to exploit this. You can't use your standard OpenCL kernels.
Thanks.
I don't know if it answers your questions.
Yeah. No, I'm asking because we are Max and me. We are in a new project where we're working on a SQL connection to
okay.
Risc. Yeah, you know this.
Okay, thanks for the question, Stefan. Answer, Eric. Any more questions, comments? Okay, I don't hear anything. So in that case, I think we thank Eric and Jerome again for the very interesting presentation.
Thank you to let us opportunity to present to you.
Yes,
also.
and we'll post the video as normal within the next couple of days for anyone that missed it. And then look forward to the next edition of the Compute Accelerator Forum in November. So thanks, everyone, and see you soon. Bye-bye.
Bye.